Today we're going to talk about solving quadratic equations by graphing. In the previous chapter we solved quadratic equations with factoring, but we can also solve quadratic equations by finding the x-intercepts. A quadratic is a nonlinear equation that can be written in the standard form ax squared plus bx plus c equals 0 when a is not equal to 0. Obviously, if a was equal to 0, then we would have bx plus c equals 0, which would be a linear equation. So for example 1, we are trying to solve x squared plus 2x minus 3 equals 0 by graphing. So you'll remember from the last chapter, what we would first do is we would find our axis of symmetry with the x equals negative b over 2a, and we would fill in the 2 for the b and the 1 for the a, and when I reduce that and solve, I get a negative 1, and this would be my axis of symmetry. Then what we did was we took that axis of symmetry, which is also the x coordinate of the vertex, and we plugged in that negative 1 into our equation. And this will allow us to find the y value that goes with it. So we end up with the negative 4 when x's are negative 1. So negative 1, negative 4 will be our vertex. And again, this was all review from last chapter. Once we have that set up, get a little more room here, we will make our table to help us find a few other points to make sure that we can see how this is working. Negative 1, negative 4 is going to be our vertex, or in this case, our minimum number. So we definitely want to pick a few points on either side. So I might plug in negative 2. I might plug in the 0. If I plug in the 0, I almost don't need to plug in anything because I already know from standard form that this number right over here is my y-intercept, which is the 0 for the x. So I know that my y-intercept is at negative 3. That would also tell me that on the other side, because of our symmetry, the negative 2 is going to be a negative 3. And then really I just have to focus on maybe one more point. So I'm going to use the number 1. 1 should be a little bit easier to find. If I was to plug in the 1, then I would look at trying to figure out 1 squared is 1, plus 2 times 1 is now 3, minus 3 is now 0. So I also know then that at negative 3, I would get that same symmetrical negative 3, comma 0. So then I'm going to go and make my graph. I draw my graph with my y-axis and my x-axis. Obviously you can use a ruler and make it a lot more neat than that. I would plug in some points. I would have negative 3, 0. I would also have 1, 0. I have negative 1, negative 4 as my vertex. And we also said we had 0, negative 3, and negative 2, negative 3. So there are my 5 points. And then I can draw my curve through those points, and that is the graph of x squared plus 2x minus 3. So from the last chapter, we also talked about how our x-intercepts are our solutions. So this question was asking us to solve by graphing. So basically I am looking at my graph for these 2 points right here. These are my solutions. These are the x-intercepts. Those will be the solutions to this quadratic. So to answer our question, the solutions x equals negative 3 and x equals 1. So on this example 2, we're trying to solve x squared minus 8x equals negative 16. Well, we know the very first thing that we want to do is we want to bring that the negative 16 over to the other side to set the equation equal to 0. And again, then we're going to use from our standard form the x equals negative b over 2a. Notice this time that it is negative 8 over 2 times the 1. The two negatives are going to cancel to make a positive, and so that our axis of symmetry this time is going to be at x equals 4. Okay, so again, if I'm going to draw my axes, this time I can see that I have x equals negative 4 is going to be my axis of symmetry. Then what I'm going to do is take that 4 and plug it back into our equation. To find out what is the y coordinate of the vertex. And I'm going to get 16 minus 32 plus 16, which is going to give me a 0. So that will tell me now the y coordinate of our vertex. So our vertex is going to be at 4, 0. So that will tell us right here is the vertex at 4, 0. And again, if I'm making my table by graphing, that will help me center where my table is going to be, because that gives me a good starting point that I just need a few points around that. If I plug in the 3 and I run it through that equation, I end up with the y's are a 1. If I push 5 through, I also get a 1. And then if I do 2, I get 4. And 6, I also get 4. So then I can plot those 2 points. There's 6, 4. There's 5, 1. 3, 1. And again, I can draw a nice smooth curve. And that will be the equation that we are graphing. Now notice here, our solution is actually, there's only 1. Because now we only have one x-intercept. So again, our solution to this question is x equals 4. So notice that this graph only has one x-intercept. And notice this time there is only one answer. Now some of you may have noticed way back up at the top that x squared minus 8x plus 16 is actually one of our perfect square trinomials. So I could have actually factored this one, which is another way of solving some of these, and gotten x minus 4 squared. And obviously x minus 4 times x minus 4 would have been just one solution because they're both the same. And when I used my zero product property, I would have gotten x equals 4 that way as well. So there's certainly more than one way to do these, which we're going to see throughout the rest of this chapter as well. But this is one way to do it if you were to make the graph. You're looking for your x-intercepts. So here on example 3, again we're going to be solving by graphing. This time what I'm going to do is move my negative x squared over to the right. Basically because there's one less move than I would have to do if I was trying to move both the 4x or the 5 over to the left. So now we have it into the standard form of x squared plus 4x plus 5. So again, we're going to use x equals the negative b over 2a to help find the axis of symmetry. This time our b is a 4, and we are still doing a 1 for our a value, so it's 2 times 1 in the denominator. And when I do that out, I get a negative 2. Again, that is where our axis of symmetry is, and that will allow us to start drawing our graph and starting to see some of the information that's going to help us with the solution to this quadratic. So when I look at negative 2, that tells me that we're going to be coming right down this line at some point. The a value in the front means that we should be opening upwards. And what we're going to do next is take that negative 2 and we're going to plug it into x squared plus 4 times the negative 2 plus 5 to find out the y value that goes with it so we can figure our vertex out. we get 4 minus 8 plus 5. 4 minus 8, negative 4, plus 5 is a 1. So that is going to tell me that the vertex for this quadratic is going to be at negative 2, comma 1. So when I plug in negative 2, 1, there is our vertex. We also know that from standard form, our y-intercept, which is back up here, is the plus c value. So I also know that one of the points that I don't have to worry about finding on our table is 0, 5. So 1, 2, 3, 4, 0, 5 is one of our points. That is your y-intercept. Then again, from the axis of symmetry, I can come to the other side here to show that at negative 4, 5 is another point. And really all I'm trying to focus on at this point is just one more. So I know that it's negative 2, negative 1 to center my table. We just jumped a little bit ahead to get to the 0, 5. So I'm just going to focus on negative 1. And if I put negative 1 in, I get negative 1 squared is 1, plus negative 4 is negative 3, and then a 2 to get the other side to get to negative 1, 2. And again, through our symmetrical knowledge, we know that we have that same negative 3, 2 also on the other side. And then what you just need to notice here is that when I draw my graph, we do open up, like the a value says. We do have our vertex, our axis of symmetry, we have our y-intercept, but what you're going to notice here is we don't have an x-intercept. We don't have anything where our graph is touching or crossing over the x-axis. So when this happens, what we say is that we have no solution. There are no x-intercepts. So anytime you draw a graph, you are looking for your x-intercepts, which are our solutions. Those are also going to be either one point, which we saw in example 2. There are going to be 2 points sometimes, which was example 1, and in this case it does not cross. So when that happens, then we say that there are no solutions. And I think just to summarize everything that we've talked about, this is kind of a good picture. These are the examples that we just did. Example 1 is the first one on the left. When our parabolas cross twice over the x-intercept, that would mean that we have 2 real solutions. When it only has the one point that is our x-intercept for the vertex, that is possible, which gives us only one real solution. And there are times when our graph does not cross over the x-intercept, so there are no x-intercepts, which means there are no solutions. And then down at the bottom, just want to be another reminder that when we are looking at these different terminologies, we sometimes talk about our solutions as roots. We also know that they are referred to as x-intercepts. We've also talked about how they are all zeros. So I just want you to notice how all of those terms are really referring to the same thing: solutions, roots, x-intercepts, and zeros.